Okay, we'll try to keep this somewhat short. Of course, we have to, just on account of we got this shortened class period. Okay, page 80. So 80. Okay, so what we worked on yesterday, we still have a couple compounds to go over. Potassium iodide and what was that, magnesium phosphate, I think. Those were the two. Okay, so on page 80, it's talking about relative atomic masses, and that's what we've been working on. That's what you're obtaining or reading off of the periodic table, which I have copied for you. Oh. Oh, you passed these around? Oh, well, one. It's not like it blends in with that desk, I guess. All right. Everything in, we won't go that far. That's important. Okay. So everything you read off of here, it's going to be an average atomic mass, whether it's 1.01 for hydrogen or 55, I don't know, 0.85 for iron. Is that right? Yes. Okay. So that's what we call an average atomic mass. So on page 80, okay, masses of atoms exposed in grams are very small. As we shall see, an atom of oxygen. Now, why do they say oxygen 16? What do you suppose 16 means? That's the average atomic mass. So rather than saying 15.9999, you would say 16. For example, has a mass of 2.657 times 10 to the negative 23rd grams. For most chemical calculation, it is more convenient to use relative atomic masses. Okay, if you would have read in chapter 2, we've skipped over that. We want to start with the important material with this and get started with utilizing scientific notation here, which is what that 2.657 times 10 to the negative 23rd is. Have you done that in Algebra 2? Some of you, is scientific notation familiar? Does it look familiar? Some say yes, some say no. All right. Yes. Okay. Okay, so in order to set up a relative scale of atomic masses, one atom has been arbitrarily chosen as a standard and assigned a relative mass value. The masses of all other atoms are expressed in relation to this defined standard. And of course, as you can see, it's what we call carbon-12. Okay? The standard by which scientists compare this unit of atomic mass is the carbon-12 atom. It has been arbitrarily assigned a mass of exactly 12 atomic mass units, or 12 AMU. In our cases, we would say 12 grams. Okay? It's 1/12 the mass. Sorry, I went too far. One atomic mass unit, or 1 AMU, is exactly 1/12 the mass of a carbon-12 atom. Okay? The atomic mass of any atom is determined by comparing it with the mass of carbon-12. The hydrogen, or H1 atom, has an atomic mass of about 1/12 that of carbon, which would make sense. I mean, hydrogen's 1.01 and carbon is 12. Okay. The precise value of the atomic mass of a hydrogen 1 atom is 1.007825 atomic mass units. But what we did yesterday, when we utilized that of hydrogen, we said what? 1.01 to the nearest hundredth. Okay. An oxygen atom has about 16/12 or 4/3 the mass of a carbon-12 atom. Useful measurements show the atomic mass of oxygen 16 to be 15.9949. That's how we arrive at 16. The mass of magnesium is 24, and we could go on so far and so forth. So that's where those numbers were calculated. It just says arbitrarily atom number 12, okay, or carbon 12 was utilized for that. Okay. Now, next I want to go over to page 83 where it talks about the mole. So mole is a very vague term. What do you think of when you see a mole? There's three things that come to mind. This in chemistry, something on surface of the skin, or in, is it a spy? Is that a mole as well? And four things, then the animal. Okay, top of page 83, the mole. The mole is a SI unit for amount of substance. A mole, abbreviated as MOL, is the amount of a substance that contains as many particles as there are atoms in exactly 12 grams of carbon-12. The mole is a counting unit, just like a dozen is. We don't usually order 12 or 24 ears of corn. We order 1 dozen or 2 dozen. Similarly, a chemist may want 1 mole of carbon or 2 moles of iron, okay, or 2.567 moles of calcium. In the sections that follow, you will see how the mole relates to masses of atoms and compounds. And you can use that in measurement as well. For this desk that was made, okay, would you want to deal with inches on this desk or feet? Okay, if we use feet, it's 8. If you use inches, it's 96. So which number would be much easier to deal with? 8 would be. So it's just a counting unit, just like a mole. 8 feet or 96 inches. This next number is what we call a constant. You have dealt with constants before, you just have never realized it. From 2 years ago, can you think of a constant that you utilized in physical science? 9.8 meters per second squared, which is acceleration due to what? Right. And I had a circle up here. If you wanted to find the distance around a circle, at some point you have to multiply by what value? Which is also a constant. And what we see here, Avogadro's number, is also a constant. Okay? So on page 83, the number of particles in a mole has been experimentally determined in a number of ways. The best modern value is 6.022, and we won't use all those digits, that's where we stop, times 10 to the 23rd. This means that exactly 12 grams of carbon contains 6.022 times 10 to the 23rd carbon-12 atoms. Okay? How big is an atom? Yeah, at the very most, it would be that big. So what we're putting in relation here, the size of the atoms is so small that you need to utilize a number that big to correspond to all of those different types of atoms that you would see in there. Okay? And trust me, we'll try to make sense of this. You might be thinking, we're reading this, but this isn't helping. Okay? If it does, please be patient. We'll get you through it. Okay? The number of particles in a mole is known as Avogadro's number, named for the 19th century Italian scientist Amedeo Avogadro, okay, whose ideas were crucial in explaining the relationship between mass and numbers of atoms. Avogadro's number, as we just stated, is the number of particles in exactly 1 mole of a pure substance. All right, so what we're going to do here just really quickly, and then we're going to wrap this up because it's not fun sitting in here. Everyone would agree. We have some students who are absent. We're up to about 10 minutes, which is probably enough. So go ahead and, okay, Ki, okay, or potassium iodide, What is the mass of potassium? Okay. But I think there's a number out there that 0.09 can be rounded up to 0.10. You can? You're just saying yeah for, at least I believe so. Yes, because it's 0.098. So the 8 bumps the 9 up to 0, which bumps this up to a 1. Okay, what's the mass of the iodide ion? Oops. Okay, our simple math.
90.
Oh. Okay.
163.
I'll take your word for it. We agree?
Oh, 166. Yeah, my bad.
Okay. That's simple math. Yeah, and that happens. Okay? And then what was magnesium phosphate's atomic mass? Should be probably in the 300s, right?
Yeah.
Okay. How much was it? No, all together. All of this. What is it? 260. Oh, 260. Okay, approximately. Okay, so these are atomic mass units. So you're taking that magnesium, which was what, 24.7 times 3 gives you a number. Whatever phosphorus atomic mass unit times 2, add that together, and then 8 times 16, I think gives you what, 144. 144 plus whatever that is, plus the 2 phosphorus gives you 262.87. So this is just like a counting unit, okay? So for every 166 grams or atomic mass units of potassium iodide, you would get exactly 1 mole, okay? So now, we're going to try to make sense of that right now. We need this number. This is a little bit of foreshadowing going forward, but we'll get you through it. Okay, someone just pick any random number. 37? Okay, so if we have, the number was 37, if we have 37 grams of potassium iodide, okay? Have you ever heard of dimensional analysis? I think you probably use that in, maybe using algebra. A way to look at that is, for instance, if you have, we'll just use this number, if you have 262 quarters, 262 quarters, how many dollars do you have?
26. Wait. 262 quarters.
Okay, so this is what we mean by dimensional analysis. Okay, so this is what this means. For every 260, now you don't need to write this part down. Okay, $262. Okay, so how many quarters are in a dollar? Okay, so for every 4 QTR, you get $1. Okay, so therefore these cancel each other out. You take 262 times 4.
1048.
Okay, so if you have 1,048 quarters, okay, that means you have $262. Is anybody lost? Okay, so we're going to take this type of logic, okay, and apply it to here. So notice if we had dollars on top, where did dollars go in our second step? This is step 1, this is step 2. Dollars went downstairs. So now, if we have grams of potassium iodide upstairs, to cancel that gram out, how do we do that? We put grams on top or the bottom? Okay? We're going to put grams of potassium iodide here. You might be thinking, well, why is there a space there? This is where adding together these atomic masses is so important. Okay? So what is the atomic mass for the compound of potassium iodide? We've calculated that already, right here. So for every 166 grams of this substance, right here, we get a mole of that substance. That's why we call moles a counting unit. It's just a way of comparing one substance to another, because how do you do that with gases? Because you can't see them. Sometimes you can't smell them, you can't taste them. It's really hard to get an empirical value, but if you have this way of mathematically solving that, you can then deal with gases at that molecular level to make conversions between one type of substance and another. Okay. So, what did have the grams of potassium iodide, what have they done? What have these values done to each other? They've canceled each other out. Okay? Now, we're left with moles of potassium iodide, but we want to do this together because we want to know how many atoms of potassium iodide are present. Okay? What was that constant that we used? Avogadro's number, okay, which was 6 something. Okay? So that number would go here, 6.022 times 10 to the 23rd atoms for every mole of that. So this is just a conversion factor from atoms to moles. For every set of Avogadro's number, it gives you a mole of that substance. Okay? So what do you suppose these moles have done with one another? They've canceled each other out. Okay? Now, does anyone think they want to try to tackle this on their own? How to punch this into a calculator? Or should we do it together? Do it together. Okay. So, for some of you, if you have a calculator like this, okay, we'll get you through it. I think when I walked through the room earlier, there's maybe 2, maybe 3 students who don't have one like this, okay? They might not quite be the same way that you calculate these, but we will do our best to get you there. Okay, if numbers are next to each other, you multiply. If they're on the bottom, you divide. Okay, so to start this out, we'll wrap this up here right shortly. Punch in 37, okay? Hit the multiplication button, because that's what we're doing. These are next to each other, although this is a 1, but any number times 1 just gives you the same thing, right? So it's not that we're skipping over it, we've accounted for that. 37 times 1 times 6, decimal point 0, 22, okay? See this second button? Hit that. And then you see this x to the negative 1? What does it say in blue right above that? EE. That means exponent. Scientific notation means you're putting an exponent in to make it more convenient for yourself. So once you've done that, you see where it pops up as an E? Now you know you're in the scientific notation function, and you just hit 23. Go ahead and hit equals, and you get 2.22 times, well, there's some other numbers, but 2.22 times 10 to the 25th. Yeah, it would be 2.23 times 10 to the 25th. So we still have this 166 to deal with. So we just take this number, divide that by 166, and you get 1.34 times 10 to the 23rd. Okay? This is what scientific notation is. Okay? Technically, you don't have to use this. You can do this if you wanted to. Okay? Now, we've got to do, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay? If you don't want to use scientific notation, you don't have to. You can punch this number in instead of that one. It looks a heck of a lot more convenient, doesn't it? Okay? But don't fall into this trap. This is a different function. This is a what? The caret symbol, right? Don't do that. Don't use this caret symbol. These are two totally different functions. If you do this, you are taking this number times the 23rd power. If you do this, it's just telling you how many times you've moved the decimal place. Okay? This is a multiplication function. This is just a movement function of the decimal. Different functions. Like I said, don't use the caret. It's an easy trap to fall into. That was a lot of information in a short amount of time. You might not even know what to ask. Is anybody just totally lost?
What does the number, after we punch it on the calculator, what does that number, what is it?
It's atoms of potassium iodide.
Atoms per gram?
Nope. Atoms total.
Okay.
Yep. All right.
So,
Okay. I think for recording purposes, we'll stop there. We'll pick up with this a little bit tomorrow. I'll come chat, walk around, and work with you people. We'll stop there. We'll see you next time.